This is the beginning of second hour's questions. We just went over the difficulty of the test and the fact that you get a piece of paper before taking the test. Before we get going here, oops. Okay, and there, there, there. Okay. Now I'm going to write them down, but because I can write them shorter than this is up here, but ultimately I'm just going to be writing up here. Before the test, we will always do something known as the tweaky-wee, or come on, do the thing. Cool. Things I would know if I were you. The tweaky-wee. Hopefully in the future I say, like, it's that time again, and everybody goes, tweaky-wee! Okay? And it's just meant to be a dumb, jokey thing on the day when there's a lot of stress. So we'll try to work on that. Okay, number one. Definitions of position, displacement, distance, clock reading, time interval, average velocity, constant velocity, speed, instantaneous velocity, and acceleration. I mentioned this before, I'll say it again. When we're in a chapter like this, it can make you think like, we're getting to the end, we do a lot of math, and you're like, oh, that's what this test is entirely going to be. No, we did that quiz already. It was called the problem quiz, where everything was problems on there. Okay? And that kind of let me know roughly where you're at. By the way, in general, really happy. Really happy with that quiz. I mean, nobody aced it, and I'm still really happy with exactly where we're at right now. But to that end, people forget about the stuff earlier in the chapter. One thing that I highly suggest, and I've said this before and I'll say it 1,000 times, read the book. Okay? Learn how to read the book. I don't mean read it like Harry Potter, read it starting at the beginning and move to the end. Especially at this time of the year, what you should do is you should go to the chapter, you should go to the end. At the very end, it has key ideas from the chapter. You should basically go to that and just kind of go down and do a checklist for yourself. Do I know that? Yes, no. And when you get to know, then you go back and read that section. Be targeted about your reading. I'm not asking you to waste your time on this to read something you already know, but listen, these are experts in their field that have written this particular text, and it's super helpful to remind yourself of stuff that we did 3 weeks ago when talking about these particular definitions. Number two, average velocity and constant velocity problems. It's been a minute since we've worried about those, but you need to know how to do them. Number three. All right, so I'm going to say kinematic equations, but I'm also going to tell you that technically there's a little bit more to it than that. Whenever I say the kinematic equations, I'm always referring to those four, and those four are when you accelerate, but also know that technically the constant velocity equations that we have up here, number two, are kinematic equations. Kinematics means study of motion, so really kinematic equations is any equation that has to do with that motion. But since I already did the when it's not accelerating, I should probably talk about when it is accelerating, so let's just put accelerating here. Okay, and then finally number four, x versus t, v versus t, and a versus t graphs. These are the skills. With the remaining time today, usually what we'll do today is you'll just ask questions. Just over and over ask questions. First part, I'll always start with conceptual questions. Honestly, these are usually the most valuable for people because I'm happy to do problems. You're welcome to ask me to do problems, but 2.6 is good for getting ready for things, but also like that's not like kind of the difficulty of a lot of the problems, and also that exact problem is not going to be on the test. So if I do even go over it, I'm probably not going to finish it. I'm probably just going to make sure that you understand what you should be looking at. But questions? Yes.
So when you do the x versus t, v versus t, and a versus t graphs, could you just kind of talk a little bit more about like when you have like values, how do you know where to put them on like graphs? Like
Sure, I'd be happy to. Because I'll be happy to specifically because it relates to this, the difference between these guys right here and these guys right here. And I think instantaneous is going to be on there. I'd be happy to do that, okay? But I'm probably not going to use exact numbers. And also, I wouldn't even answer this question because it's definitely not going to be on the test specifically like that, okay? The only reason I'm going over it is to understand these a little bit better, okay? So let's take, for example, like the rocket problem. In the rocket problem, there was about 3 sections of the x versus t. There was, hey, the rocket is speeding up, okay, in 15 seconds. And then this next section right here, it's going to the very top, okay? And I don't remember the exact numbers, but I'm going to make something up. I think the displacement of the first section was something like 2,250 meters. You have to remember that displacement is how much it changes, right? So on the graph, of course, we're going to start here at 0, probably because you set your 0 there. It'd be weird that you set your 0 10 meters down below the ground. Okay, so that means this spot right here would be 2,250 meters. Okay, now what's important though is let's say displacement 2, it wasn't this, but I'm just going to do it for simplicity of math, it was like 4,000. Here's what people get wrong. They go, oh, that spot there is 4,000. No, it wasn't. Why not? Yes, 8.
Because it was asking for like the total displacement, so it'd be those two numbers added together.
Not the total displacement, you got the right idea. This is position on the x-axis. This is not displacement at all, right? Displacement is the change in position. So what's my initial position when I start here? 2,250. So my change in position should make this guy up here 6,250. Why? Because that is position and not displacement. Got me? On the other hand, the first time interval right here was 15 seconds. It was told you directly in the problem. And if I'm not mistaken, I think the other one was 30.2, but I'm going to round to the 30 to be simple. Again, it's a big time, so people just want to put 30 over here, except that's not the final time because this is clock reading, right? That's like saying like, hey, the class started at 1 o'clock. And Spainhour talked for 20 minutes and then he talked for 30 minutes. So what time was it after the end of the second one? Oh, it's 1:30. No. He talked until 1:20. The clock reading was 1:20, and then another 30 minutes later means now it's 1:50, right? So this time here should not be 30 seconds, it should be 45 seconds. Does that make sense? Those are usually the biggest struggle on here. Beyond that, like I'm just doing the first 2 sections because I think there was this back half over here. Your velocity versus time graph should have looked like this. I'll show you where people make the biggest mistake on this one because I think it's particularly helpful. Okay, let's actually do a tick mark there. Yes, and so tick, tick, tick. First section almost everybody gets, no problem. It's pretty easy. It's just a positive acceleration like that. Okay, it's a positive 20. And then actually, I was a little bit more careful with this tick. Come on, there we go. It should technically be over like here to help us out with this understanding. But then we do this, and people stop because it's back at 0. Except should the velocity be back at 0 at the very end? No, when should it be back at 0? Right here. And then what should the velocity do in that last amount of time? Yep. The big thing that people miss is that on the backside. I don't know why it may be so darn big, but that in this particular case, I think that the thing sped up to 300 meters per second, which means that's 300 meters per second at 15 seconds. And then obviously over here at 45 seconds is when it crosses 0, right? And then whatever time it was, I don't even remember. I believe it got down to like negative 366 or something like that. That's all you need to do is put it on the axis right there to signify that boom, boom, that's negative 366. And finally, I don't know why it made me so big. I really don't. All right, let's fix that on the last one. Acceleration graph. All right, cool. We fixed it. All right, so for the last one, see, it's funny because I made it worse. It's fine. That's not funny. It's a good point. It's a really good point. I should be set my expectations correctly. If it's not funny, don't laugh. All right, cool. All right, so up here, we started at 20 meters per second squared for 15 seconds. And then in the remaining time, it's always just negative g. Does that help? Cool beans. Other questions? I've said this before, I'll stand on my soapbox again. Ask questions. My ideal class is full of, currently we're at 19 people in here. 19 different questions caused by 19 different people. If you are not in a class willing to ask questions, two things are the case. One, you perfectly understand the material, or more likely you're afraid. And that second one, specifically to my introverted people here I'm speaking, I understand. I get it. It sucks. And the best piece of advice I have for you, which I think somebody should have told you a while ago, and I'm sorry that they haven't, is you have to get over it. You have to ask questions. Difficult classes require people asking questions. If you don't ask questions, okay, and I know there's a 3 up and I'll shut up in just a second. If you don't ask questions and you get a bad grade and you come to me and go, why did I get a bad grade? That's the first thing I'm going to put back on you. Why didn't you ask your questions? Did you know? Did you think that you perfectly knew? Or were you hoping that someone else would ask the question? Because it's not their responsibility for your education. You guys are all going to leave here. Most of you will all go to entirely different, 19 different colleges for the most part. Some will double up. But you will not get to stand on them for your education and must learn to ask questions. My Physics 2 kids right now, the best at asking questions. Why do they make it to Physics 2? Because they're the ones that are asking the questions. Usually Physics 2 is entirely involved with people that are regularly at 7th hour physics in Physics 1. You don't make it if you don't ask questions. I don't care how smart you are. My apologies. Tessa, you first.
So I just had a question about what would be on the quiz. Will we ever have questions about like labs we do?
Excellent question and a great one. And thank goodness for you that you asked it, because so many of the people didn't know that and didn't know they needed to. Yes and no, but only in concept. Okay, like only in like understanding. We kind of keep a little bit of labs and tests a little bit differently because labs take a while, and quite frankly, labs kind of need your mind to sit in it for like 3-4 hours to write that lab report. So things like graphing and linear regression are definitely not, it takes a lot of time. That's meant to be on a lab, not going to be there. Stuff like understanding like how you got to the 1/2 acceleration, okay, as opposed to just acceleration, could possibly be on there, probably in multiple choice and done relatively quickly in that particular way. Excellent question. Yeah.
Can we go over number 5 on the 2.6 kinematics?
Sure, would be happy to. I'm going to wait on problems just a second. I'm going to remember that up here to see if there's any conceptual stuff left. But then absolutely we'll do that. Yes.
Could you just briefly talk about the 1/2 acceleration, just to?
Sure, absolutely. So whenever we graph, we are graphing what is what the real world says is this. Okay. And then when we make equations, the equation is meant to model essentially that graph. It's meant to model that. Now, I developed the equations from an algebraic stance of talking about, okay, this is the definition of acceleration, this is the definition of average velocity, and we put them all together, and we got those 4 equations, blah, blah, blah. It was a day. Honestly, for some of you in here that continue on in physics, you're going to want to go through that day like 2 or 3 times before you're finally like, oh, point being, okay, anytime we have a graph, there's an equation that specifically goes with it, okay? We, in that lab, set initial velocity at 0. We were trying to find acceleration, trying to measure, actually it was positive g at the time. Okay, we said we were going to measure time, and delta x was going to be set, meaning these two right here are the variables in that equation. Since those are the 2 variables and those are the 2 constants, the equation that perfectly embodies that goes with that was this equation right here. Now, using the stuff from chapter 1, actually, hold on, 0, so, okay? Using the stuff from chapter 1, you should now be able to take that equation and go, okay, that's the equation that goes with our graph because of what we did over here, okay? And you should be able to do the following. You should be able to go, all right, if Spainhour's right, and reality says that that is the equation, then these are the things I should see. And the things that you should see are 1, parabola, because of that right there. Okay? And then, since it's a parabola, let's lay this out. Y equals kx squared plus b, the generic equation of that parabola. Okay? And from that, we see that our x squared is right next to the k value, So what is the k of that graph? 1/2 of whatever the acceleration is.
So it's kind of there in a sense. It's just not like it's there. It's just already multiplied to that k value, basically.
Yeah, sort of a way to put that. Yeah, I mean, well, the k value is the 1/2 a.
Yeah.
Right, the whole thing is already in
Okay.
that. We can get more and later kind of talk about, okay, why is that actually the case? It has to do with average velocity. It has to do with the fact that you're speeding up to this other thing, and so you're covering more distance over time. And like I said, we can get to that a little bit later. But yeah, that's ultimately your reason. That's why k is 1/2 a. It's just simply that equation perfectly goes with the variables that we did, and x squared means it's a parabola, and k is right here, and b, of course, should have ideally been 0. It's never perfect because of error, blah, 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 blah. Yes, Ken's
Like a basic reason, the difference between average velocity and constant velocity.
Ooh, I could do more than that. We should 100% cover this real quick because that's definitely a good conversation to be had. As well as one you didn't ask, but I'm going to extend beyond that. Average velocity versus constant, and velocity versus speed. Okay? Specifically because I definitely know there's a problem on the test that handles this guy right here. But average velocity versus constant velocity. All right, let's give you some numbers here. Let's imagine. Well, I'm going to walk across in here, but for the sake of people in first hour looking at it, this is Spain. We're walking across just the front of the room. Now, I'm going to walk across the front of the room, except I'm going to do this a little bit wonky. Maybe walk is not the right word. So I'm going to start right here. I'm going to look at the tile I'm on, so I can measure a little bit later. And Spaino's going to move across the front of the room. 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000. Okay, we'll stop at about 6, 1,000. Was my velocity constant? Definitely not. Absolutely not. And that would be very, very hard to measure because Spainhour had like 7 different accelerations in there, which would cause a piecewise function of 7 different things. I went through a bunch of crappy math. For what purpose? Well, if we modeled that motion, what we could probably do instead is, rather than worry about his back and forward and whatever, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. He went 18 feet in 6 seconds. So on average, he went that way at about 3 feet per second. Okay? What does that mean? If you kind of relay the ghost run, okay, sorry, video game talk here, okay, the ghost run of Spainhour being ridiculous, and then have Spainhour walking at 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000. That was a model of the average velocity, and both the walking Spainhour and the ghost Spainhour would have gotten exactly here in the exact same amount of time. Yes? So average velocity is a tool. Okay? Now, in that second run you just saw, you might notice that I was traveling at a constant velocity, right? That constant velocity and the average velocity of it are exactly the same, right? Why? Because if you checked at any point in time and stopped and measured me at any point in time, I would have been moving at 3 feet per second. 3 feet, 3 feet, 3 feet, 3 feet, 3 feet, 3 feet, 3 feet. Yes? Whereas the first time, times I was moving at +6 to the right. There were times I was moving at -2. There were times I was moving at +7 or -1. We add all those up. What should we find? We should find that the average of all of them together is 3 feet per second, but it's way, way easier to just take the total displacement and divide by the total time. Does that help a little bit? Okay, let's talk about velocity versus average velocity. Okay, I'm going to pick some easy numbers here. Let's say Spainhour goes this way 8 meters and then comes back 2 meters. Okay, the whole process takes him 4 seconds. Quickly in your group, tell me what his speed is and what his average velocity is. Discuss quickly in your group. You should be able to, these numbers should be allowed to go quickly in your head. Actually, I'm gonna make this. No, I'm gonna make this 2 into a 4. Shouldn't change your answer very much, but go ahead. Again, what is the average velocity of Spain-hour, and what is the speed of Spain-hour in this case? I'll write their definitions on the board in case it helps. Average velocity, speed. All right, so what you got? What's the answer for speed? 3 meters per second. Why? Speed deals with, look at the equation. Speed's dealing with what 2 things? Which is, what is the absolute value of delta x? Distance. Do we give a crap about what direction it's going? No. How much total space did Spain-hour cover? 12 meters. How much total time did it take? 3 seconds. 12 divided by 3. Sorry, 4. I apologize. 12 over 4. 3 meters a second. Does that make sense? Okay. Average velocity. What's that?
Why do you have a 2 next to the? Oh, is that equal sign?
Yeah, sorry, that's my bad. My apologies. Trying to go quick up here and this thing registers it incorrectly. My apologies. Yeah. Okay. What's his average velocity then? 1 meter per second. Now, what does that 1 meter per second say? It means that if we had another Spain-hour do a ghost run, okay, definitely too tall, but we're not going to worry about that right now, and travel this displacement at a constant rate of 1 meter per second, should they get to the same spot at the exact same time? Yes. And the other way to say this is, well, are they traveling faster than that? Of course, they were traveling 3 meters a second. So why is it only 1? Because we have to balance the positive 3 meters per second in this 8 meters with the negative 3 meters per second over here. Or here's a better way to put it. Let's change this problem carefully and instead make Spain-hour walk all the way back to where he began. Let's use the exact same time. So it's 8 that way, 8 back. What is his speed? He's going further in the same amount of time, so it should increase. 4. What's his velocity? 0. Okay? Why? Why the heck? That doesn't make sense. Well, was I going in a positive direction the exact same amount of time I was going in a negative direction? Yes. And don't forget that vectors and scalars do entirely different things. Scalars don't give a crap about direction. We just want to know what the number is, know what the number is. Vectors, important thing is to tell you where the object ends up. If we have the ghost Spain-hour run that velocity, is he going to end up at the exact same spot as the other Spain-hour in the same amount of time? Yes, he's not going to move. His average velocity is 0. Okay? Now, the important thing here is this. On a test, a student reading a problem quickly will read the problem and pass over very quickly the word speed or velocity, treating them as synonyms. There should be red flashing lights and giant sirens going off in your head the moment you see one of those. Boom, 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 boom. Those are very much different things. Okay? I've had students come back to me before and be like, "That's a trick question. Only if you don't know what you're talking about." If you don't know what you're talking about, then yeah, it's a trick question, and I slid it in there. If you know what you're talking about, you know the importance of the difference between these two things, and it's not a difference at all. So if that happens on the test, you see one of those, you can maybe highlight it, feel free to circle it, or put something in your head to let you know that's what you need to be dealing with. Yes, sir?
Would speed be talking about like the average speed of the situation?
Yes, it's technically the average speed of the situation, but we don't worry about getting into the problem with that. Also, don't let me forget, we need to talk about aqueous solutions and magnitudes.
Oh.
All right.
I
Well,
contract with.
oh, fair. Okay, you got yours. All right. Yes. Other questions or about this?
How do you get 2 meters per second?
What's that?
How do you get 2 meters?
Well, originally, I think I changed some of the numbers. If you didn't see that, by the way, I had 8 this way and 4 back, right? So a total of 12. Took 4 seconds. 12 divided by 4 is 3.
Okay.
It's just these equations appear to be similar, and they're not. Distance just says, hey, don't worry about direction. So plus 8 plus 4 is 12. Divided by 4 is 3. So that would be 3. Right?
So is displacement not like position final minus?
It is.
Initial?
But it's also the change in space in a particular direction. So that was talking about speed a second ago. Make sure we're being clear about this. This is speed. This is the scalar. Doesn't worry about direction. This is velocity, which does worry about displacement, in which case if you're doing this math in your head, it's positive 8 minus 4 for a total displacement of positive 4. Positive 4 divided by 4 tells us our average velocity is plus 1 meter per second. Excellent question. Other questions? Conceptual or otherwise? We can talk more about, let me bring up the other slide again here real quick. We can talk more about any of these. Yes?
I want to look at the problems list. If we could do a problem where, like, you have to find velocity or something, but then you have to find the distance from, it'll go up and then it'll hit the ground.
Sure. Okay, so if I'm not mistaken, it would be something like, I'm going to talk about this conceptually very quickly because I think I can do it kind of quick. An object is thrown up with an initial velocity, so it's going to go from here and go to there. Yes? Okay. This could be tackled in two different ways. Okay. If you struggle in this class right now, I would suggest the first way. And the first way is simply split it up, going up and coming back down. Okay. But understand that you're doing that because if I ask you on the test for the total height, well, then you just need this section right here. But if I ask you for the total time, I'm literally talking about the unladen swallow problem right now in the quiz, then obviously you need the total, right? So the picture can be helpful there. So if you need time, then you would need to find time in this set of variables and time in that set of variables and add them together. Okay, that's the first thing that you could do. The second thing that you could do the second thing that you can do is go, hey, let's not split it up, and instead just say, there's the displacement, right? If that's the case, then when it's here is your initial velocity, when it's there is your final velocity, and your set of variables looks a little bit different than this one. Like this one would have whatever the initial velocity is, let's say it's 5, just making something up, positive 5, so 0 up is positive. Acceleration is negative g, and displacement we don't know, but in this one, the velocity final at the top is 0. Units done. Okay? That would be your initial set for this, right? That one over there would have an initial of 0 and an acceleration of negative g, but you'd probably need to find the displacement by knowing how tall it was to begin with, blah, 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 blah. Okay? This guy over here, though, doesn't worry about the top at all. Its initial velocity is still 5 meters per second because that's the exact same spot in both. Acceleration at the same time is negative g, but unlike over here, we didn't know this displacement. Assuming, by the way, let's say it starts above the ground like 1.5 meters. Okay, so it starts 1.5 meters above the ground. We don't know this displacement at all, but we would know that the displacement in this case is negative 1.5 meters. Does that make sense? If you split it up like this, you would have to find, if you wanted total time, this time here would be the time going up. And then you would need another set of variables. And this time here would be the time going down. So your total answer would just be that plus that, right? On the other hand, if I set my equation up like this, where this is the initial and this is the final, this time is your answer. It's the combination. And if you do it either way, and if you want to prove it to yourself, you certainly can. If you do it in either style, you should get the exact same answer both ways. Okay. Any other questions? Okay.
So you were talking earlier about the difference between speed and velocity.
Correct.
So when you're doing it, like when the kinematic first problems, and you're setting up the 5 variables, what do you do if the problem is asking for speed?
We're never going to have those two kind of overlap. When we are talking about speed in here, we're almost always going to be talking about just like constant velocities and average velocities. The 5 variables specifically comes up when something is accelerating. Okay, so we are not going to have to worry about that in that particular case. I mentioned this the other day. Fine. I mentioned this the other day, but
It's right next to your speaker.
thank you. Appreciate it. I'm going to have somebody just like track it the entire time so I don't screw this up in the future. But when you do this, and a thing is going constant velocity, let's like say I was like walking across the room at 2 meters a second, you fill it in like this. And what I said was all three of those are really saying the same thing. So what I would suggest you do with a constant speed or velocity problem is go, yeah, no, we're not doing all five here, because really all that says is this right here. Now, why do I have three variables in that case? Well, it corresponds directly to the equation that you're using, right? These five have to do with kinematic equations, all of which are made out of four variables. You need three to get four, right? These three are just this equation right over here that we were using just a second ago, in which case you need two to get the third. But if we're dealing with speed, we're dealing with this one. Okay? Yes. Then we'll go to number 5 next.
Okay. Is there going to be anything about the Fermi estimations and the?
Excellent question. I believe I told this the last hour. I'm pretty sure this is true. If it's not, I'm going to look through it to make sure, and I'll shoot you a message otherwise. I don't think anything from chapter 1, technically like graphing or Fermi. The only thing that may be on there, because it's on like everything, is like unit analysis stuff, like, hey, what are the units of this? How do the units get changed? That type of deal. But nothing outside of that. Nothing that was in like the chapter 1 quiz was meant to kind of like, look, it's kind of a test, sort of, blah, blah, it's a quest, blah, it doesn't matter. Point being, like that is its own thing. We're going to use those skills throughout this course, but the focus should be on chapter 2, specifically kinematics, or ideally, like we just said, this set of topics over here.
Okay, so it's like it's already going to be incorporated in it.
Correct. Correct. Yeah. Yes, you should know those. So, in other words, are you definitely going to have to do conversion probably somewhere on here? Absolutely. I assume that's going to be done somewhere over the side. You definitely want to show that work. Oh, brings me to an excellent point. Work. Okay. So, a couple of strategizing things about my test. One, somebody asked this last hour. I think I've said this before. System of equations. 2 equations, 2 unknowns. 3 equations, 3 unknowns. Is it on the test? Yes, but it's bonus. Okay. And it's not worth as nearly as many points as everything else. Do not even touch it if you don't get everything else I've done. The second thing I want to say is all of my problems are front-loaded in points. Okay, I grade absolutely partial credit because, as you well know, you can go through these giant problems and do 20 things right, and the 21st you get wrong, and you get the wrong answer. If that's the problem that you're going through, you're going to get at least 9 out of 10 points in that particular case. You're getting most of the points. Like if you forget to square something, okay, you'll probably see me write CALC means calculator, meaning everything else. The work is great. You just calculated it wrong. Take off a point. Okay. Another code that you're going to want to know is this, that potentially some of you have seen before. RAW number means right answer, wrong number. What that means is you made a mistake earlier, so you got the wrong answer out of that, but then you use that. I then take that number and recalculate everything in your problem to see if you got technically the right answer with that wrong thing. And if that's the case, I write RAW number, which means you don't miss any more points just because you missed that earlier. You do have the wrong answer, but it's okay because you did most of that stuff, if that makes sense. And the last thing I'll say on this, like I said a second ago, is all my problems are front-loaded in points. I taught you Jafeeps for a reason. I expect given, I expect find, I expect equation. I don't care if you get the problem perfect. If you don't show the work, you're missing a lot of points because I am grading the work. I am grading your thought process, not the final answer, if that makes sense. So for my people that don't show work, just hear out what you just said. I don't care if there's the right answer. I'll still take off points if you're not representing yourself well. To people that struggle maybe a little bit more in here, that also means you do not need to get to the end of the problem to get a bulk of the points. Main thing out of that is do not leave problems blank. Time and pacing on this test. Multiple choice is very important. It's 10 problems. It's probably going to be like half the points. And I can't really give partial credit on multiple choice. I would suggest you take about 15 to 20 minutes. That might be longer than some of you might think. Okay. You can do shorter than that if you know it pretty well, but usually early on people don't pay enough attention to the multiple choice and then lose a lot of points in that particular area. So take your time, make sure you get it right. Tomorrow I will try to do my best to put a timer to let you know when about 18 minutes has gone by. That's the only time I'll do it, but to give you an idea, kind of rough pacing. It'll be like 2 or 3 short answer. Short answer means short, okay? It doesn't mean write a giant paragraph. Now you want to write until you have the right answer. Sometimes that's 3, 4, 5 sentences. Sometimes that's 2 words. You write until you have the correct answer on short answer. That's probably going to be about 3 problems that we're going to do. I think that gives an idea of the pacing as well as kind of, we talked about front loading points. Don't leave anything blank. Okay, number 5 on 2.6.
I wanted to like
me about the concept of it?
Sure.
Like, find it. Why you broke it up into two separate times? Because I remember we talked about it stuff about physics.
Sure.
I just want to go over it.
Is that the, I believe I know that's the ranger problem where they're stopping
Yeah.
for the deer? Okay, yes. Okay, the ranger in the national park is traveling 56 kilometers per hour. Remind me what that is in meters per second. That's like 20 something change.
It was 15.6.
Cool, 15.6. Okay, so whenever you have a conversion, show it real quick. It should take you no time at all. But the reason you show conversions, okay, why do I have to? You will make mistakes. I literally did it on the physics 2 problem the other day and wasted 5 minutes of my time. Why is this wrong? Why is this wrong? Why is this wrong? You dummy, you divided when you should have multiplied because you didn't cancel your units, you didn't show the work. You've been teaching 15 years, you think you know this. Anyway, point being, show the conversion work. But it says a deer jumps out 65 meters in front of the vehicle. What you have to be able to spot in a problem is not just go, oh, 65 meters, displacement. No, displacement means change in position of the vehicle, right? Does that mean that the vehicle went 65 meters? Well, let's read the problem. Does it say they actually crash into the thing, okay? After reaction time of t seconds, the ranger applies the brakes to an acceleration of negative 3 meters per second squared. What's the maximum reaction time if the ranger is about to avoid hitting the deer? Okay, reading this carefully. And this is kind of a harder one, but it walks you through this process. Maximum reaction time told me that, oh, they're reacting. So what's their velocity doing while they're reacting? Constant. That tells me an acceleration of 0. That alone, the fact that I have another acceleration means 2 accelerations, 2 separate sets of variables. Okay, so then I drew my picture. For those of you that haven't gotten to this problem or finished it real quick, the picture is everything on this problem. I don't know how I would have done it personally without it. Okay, you got the truck, blah, blah, blah. We're running out of time. Deer. Okay, 65 meters away. So I split it up. Now here's my picture. Displacement 1, displacement 2. Okay, what's here? This is when it's reacting, so constant velocity. So I'm immediately going to put my variables underneath here for a constant velocity, just 3 of them. The only one I currently know is the fact that you just said 15.6, right? Is that he's going to be traveling 15.6 meters during that time. The second section, he's accelerating. So I'm going to come over here. What do I know? Well, I know he's traveling initially at 15.6 meters per second. Obviously, the deer and both him want him to stop. The acceleration is negative 3 meters per second squared. Now, the moment I hit 3 variables on that, I go, boom, I can get that number. But the other piece of this given is the find. This is that Jafeep's part. What are we trying to find? The time that he's reacting, or the time he's traveling at constant velocity, or time 1 right here. When I did this initially, and this is a minute ago, so humor me, but this is where I thought of it. I had this laying out, and I go, okay, I didn't even think about this. Here's what I did. I go, well, to get this, I would need to know that. That's that right there. I could get that if I knew this. That's that right there. So I got that displacement with these 3 variables. To get that, I can see clearly from my picture, it's 65 minus what I have right here, which tells me that's how much space, how much space I have to react. And if that's how much space I have to react, then this is how much time I have to react. There you go.
And then also with that, are there any other